Hey there, welcome back. So we have been working on estimating the impact of an anti-fraud measure that was instituted as part of the checkout for a food delivery company. And we had to kind of estimate whether or not it impacted fraudulent deliveries, and it looked like it did. We were able to conclude that with a p-value of very close to 0. It had a very large reduction on fraud. But we weren't able to tell with the limited data that we had whether or not it impacted our total deliveries overall or our legitimate deliveries. But the second part of our question had to do with whether or not we thought we'd hit 1 million deliveries in a couple of weeks when we were taking a roadshow trying to garner supporters and financiers before we went public. So to answer that second part of the question, we made 2 different forecasts. One forecast used an index method. And according to the index method, it seems possible that we'll hit the 1 million mark, but if we wanted to do that, we might want to temporarily discontinue our fraud prevention strategy because it does seem to be slowing, at least in our forecast method. It seems like it might have a negative impact on our forecasted deliveries. The other method we used was creating a linear regression forecast, where we basically came to the same conclusion. We might hit 1 million deliveries, but most likely we won't if we continue to keep that fraud prevention measure in place. And so we've got these 2 competing strategies. One is definitely we'd like to reduce fraud on our platform, but the second is that in the short run, we've got this growth goal, and we think that we'll do better going public or making an initial public offering for our company if we are able to hit 1 million, because there's that nice big round number, even if it means there's a short run trade-off with fraud. Perhaps go public, then reduce fraud. So we've got these 2 methods, and it lends us to the question of which one is better. And like we did in class a few weeks ago, we calculated a variety of different error metrics. Our error, our absolute error, our absolute percentage error, our squared error, our root mean squared error. And we were able to make a table, a comparison table, and decide which forecast method has done a better job predicting the historical data. And then to the degree that we think a method that does better on past data is going to do better on future data, which is something that we believe when we think that the patterns that have been influencing things like deliveries historically are going to keep going, we choose the method that does the best job duplicating the data that we already have. Because if it's done better on what we already know, and we think that the same factors are going to influence us going forward, we think that forecasting method is going to do better in the future. So where are we headed? We need to calculate the error metrics for our index forecast and our linear regression forecast. I'm going to just walk you through quickly showing you the screens that I have, and then we'll go through getting there. So I first made a table of our index errors. I back created a historical forecast, calculated the errors, the absolute percentage errors, squared errors, averaged them all at the bottom, transferred them to a comparison tab. Then I did the same thing with linear regression. Came up with a historical forecast, calculated my 4 error metrics, which I then averaged at the bottom and added those to my comparison chart. And then by comparing either the root mean squared error or the mean absolute percentage error, I can decide which one of the 2 forecast methods did the best going forward, although they're very close. So let's do some replication. I'm just gonna go for it and break my own heart deleting these sheets, because who needs them? You do it once, and then it's so much easier the second or third time. All right, let's start with our index forecast first. It's an awfully messy tab, which is why I wanted to pause for a minute and show you where we were going to go. Let's just duplicate it. Move or copy, create a copy. Let's move it to the end. And we're going to call this forecast errors, index errors. All right, so let's get rid of the things that we really don't need right now. I don't need any of these charts. I don't need my all data parameters. Why? Because when I used my detrending for the data, and I was detrending the data, I was referencing my pre-friction parameters. So I'm going to get rid of the all data parameters. And I want to hold on to my index for just a second. I also don't need any of the future data going forward, any of that future forecast. And then just to save myself some grief, I'm not going to deal with any lines. So I'm going to get a handful of things out of the way. I'm going to get my parameters and my index table. I'm going to move it. And then I'm going to take, I don't need either of those forecasts. I don't need my detrended deliveries. I want to keep my index. And I really actually don't need any of those things. So what do I have left when I've brutally removed everything I need from all that work that I did? I have my date, my deliveries, my index. I don't really need these things, but since I've got stuff below them, I'm going to leave them. All right. What we've got to do is get to a place where we've got, oh, just kidding, not delete, insert. Our final goal here is to have a column that says historical forecast index, because that's going to be the historical forecast we made using the index method. And our detrended, deseasonalized historical forecast, if you guys remember what we did before, in our index, as we forecasted out a straight line, and that straight line was based on the detrended average that gave us 369,850 daily visitors across all days of the week and without that trend. So I'll take this number, I will place it just the values. I will copy it and I will paste it everywhere. Without a trend, without seasonality, with no other noise, in no noise, we basically think that our average daily sales are 369,850. So I'm going to go, is my next step, I'm going to move my index. And now I'm going to re-seasonalize this forecast. Haven't added the trend back yet, but I can re-seasonalize it by taking that 369, our average number, and multiplying it by the seasonal index. So for a Tuesday, we have a much lower number than that random average. Oh, it's not random, than that average. If I drag it down, we'll see that most of the time we've got high levels for Saturdays, low levels for Mondays. Wednesday is going to be the lowest. So we've reintroduced the expected day-to-day pattern due to preferences in food delivery. Now we've got to add back the trend. And that is going to get us actually to our historical index forecast. So the trend we used was that slope of 5,833, and we were assuming a day-over-day increase of a roughly 5,800. And if you remember going back, on our very first delivery that was 292,000, we did detrend it. So when I go to calculate this index, I'm going to have to retrend even my very first number. So how I'm going to add back that trend is to take the reseasonalized historical forecast and add to it a value that's equal to the time for that particular row multiplied by our slope coefficient. Command T to give it an absolute reference, sort of adding back the MX, but not the B. And now I can drag this out, and we will have a retrended, reseasonalized forecast. Before I do anything else, I want to eyeball it to make sure it looks like what I'm thinking. Let's take our deliveries and plot them. We've seen that 154,000 times. We're going to add to this. We're going to name total deliveries. We're going to specify our axis labels. I'm going to say okay, and now I'm going to add to it. What I'm going to call my historical forecast using the index method. And those Y values are here. Axis labels, do I need to keep adding them? Not really here, but it's a bit of a habit at the moment. And I'll say okay. And so we can see how well our forecast that we made using the index function tracks the expected rise or falls and somewhat matches the trend going upward. Just like with the linear regression forecast, we see that it doesn't really fill out the 2 Saturday peaks. And so if we have a good gangbuster Saturday going forward, we'll probably hit that million. But if these were unusual, which we don't really have enough data to know, then it's unlikely that we will. So there's that. Let's give this puppy a title. Let's add our legend. And so we see our total deliveries and our historical forecast using the index method, and we'll say total deliveries and historical forecast index method. There we go. That looks about right. So now we're ready to move forward. I'm going to take my historical forecast. I'm going to copy it and paste it special because I want to just remove all that. So now I've got my deliveries in row A and my historical forecast in row F. And I'm going to add my error metrics here. So if you remember, the first thing we do is we calculate the error. Sometimes it's called the forecast error. And then we calculate the absolute deviation. Sometimes it's called the absolute error or the absolute forecast error, but you get the idea. And then we calculate the absolute percentage error. And then we are going to calculate the squared error. Now these can be all roughly the same width, and that'll be handy. Okay, so our error, as always, is going to be the difference between our forecast and the actual deliveries. So the historical forecast method we used would have predicted on that first day 215,153 deliveries, which is an underestimate because there were actually 292,000. So our error is going to always be actual minus expected. And then our positive value here lets us know that the actual values were higher than our forecast. In other words, we underestimated. Our absolute deviation is just simply the absolute value of the error. Formula ABS. So the absolute value of this error is going to be equal to 77,704. It's because it's a positive number, but when I bring it down, you'll notice that the positive errors stay positive and the negative errors become positive, and this is essentially a distance in units. How far away are we in number of deliveries? We're 77,000 deliveries off here, we're 300,000 deliveries off here, we're 148,000 off here. It doesn't matter if it's over or below. To make this a slightly more intuitive, we can calculate it as a percentage. Our absolute percentage error is equal to the absolute deviation divided by our actual number of deliveries. So we were off by 77,000, and that is quite a large percentage. Don't let that zero fool you. It's 26.5% off. So it was kind of off a lot. And then our squared error is equal to our error squared. It's another way to remove the problems of positive and negatives canceling each other out when we try to get the average, but now we've got a lot of individual error metrics. How we know whether or not our forecast is good, it's going to be the one that has the lowest errors on average. And we're interested in the average of all four types. And these broad things down below are basically our most important error metrics. We've got the mean error, or mean forecast error, right? Otherwise known as the ME. And that gives us the average forecast error. It says 0. It may or may not be 0, and in this case it is. It wanted to volunteer some suggestions for absolute deviation, but we're not going to listen to it. We're going to drag that average over. And now we have the mean absolute deviation. MAD. Let's wrap these. And here, as a percentage, we have our mean absolute percentage error. And then here we've got our mean squared error. And then we're going to piggyback over here our root mean squared error. And to get that, we just simply take the square root of our mean squared error. So what does this tell us? We can sum it up by saying our forecast created by the index method has a mean average of 0, meaning that it overestimates and underestimates it about the same frequency and magnitude, so it's an unbiased forecast. So we should be over, like the big here, where we really over predicted that low Saturday, and under, where here we really under predicted that high Saturday, but the averages all even out to 0. What that means in number terms is that we're off by about 87,000 deliveries per day. So this does not seem like a very precise forecasting method, right? And so our mean absolute percentage error is 18%. We're off by about 18%. So our mean squared error is this really large number that has not much of an intuitive meaning, but if we take the square root of it, it's another way of getting back down to the distance of how far off we might be. It's similar in concept to the mean absolute deviation, where we take the absolute value and square it. Absolute value and average it. Here we square them and then take the square root. The fact that the root mean squared error is larger than the absolute deviation just means that there are quite a few places where we are off by a lot, as is seen here on this Saturday, where we're off by 90%, or that's actually our biggest error, but being off by 40 is not particularly great either. But when you're off by a lot, it has a really large impact on that squared error. Okay, that is going to be calculating the errors for the index method.